Hello friends, in this lesson we will implement a convolutional recurrent neural network to perform predictive maintenance on hydraulic system data. We will utilize high frequency pressure data from sensors to predict the status of the accumulator component, and the dataset consists of pressure readings sampled at 100 Hz from 6 sensors, resulting in 6,000 attributes per sensor. And our process will start by processing the data using spectrogram transformations, which convert the pressure signals into the time frequency representations. And this transformation is important for capturing the temporal and spatial patterns in the data. And we will then build a CRNN model combining convolution layers to extract spatial features and recurrent layers to capture temporal dependencies. And this hybrid architecture is well suited for analyzing complex time series data. And if you are ready, let's start our code. Now we will import the libraries and begin. First, TQDM. It is a library used to display progress bars for loops, making it easier to track the progress of data processing. And here random, it provides function to generate random numbers, which can be useful for tasks like data shuffling or splitting. And iter tools here, it contains functions for creating iterators for efficient looping, useful in tasks such as generating combinations or permutations. NumPy and pandas here, again matplotlib, you know that. And scikit-learn, TensorFlow, keras, optimizers, callback, etc. And here we have a librosa. What is this? And talk about this. Librosa, a package for audio and music signal processing, providing functions for loading audio files, extracting features, and visualizing spectrograms. And Librosa display. It will functions for visualizing audio data such as displaying waveforms and spectrograms. And let's look at our function here, plot confusion matrix, and talk about this. We will define a function to plot a confusion matrix, and what are the parameters? CM, I mean confusion matrix data, classes, list of class labels, title, here title of the plot and its confusion matrix, and CM map. What is this? Color map for the plot. And here we can see the normalize parts, and we can talk about this. We will normalize the confusion matrix by converting the counts to proportions, and here this time each element in the confusion matrix is divided by the sum of the elements in its row, giving the proportion of predictions for each actual class. And plotting parts, we will create head map of the confusion matrix and plot imshow part here displays the confusion matrix as an image with the specified color map, and plot title size font size here it says the title of the plot with a size of 25, and you can change these parts. And tick marks parts here, as you can see, we set the x and y axis tick marks and labels, and np arrange here it creates an array of indices for the class labels, and x ticks here it sets the x-axis tick marks and labels, rotating them 90 degrees for better readability. And plot y sticks here it sets the y-axis tick marks and labels, and here annotate plot part here. Let's talk about this. We will add text annotations to each cell in the confusion matrix. And fmt, what is this? It says the format for the annotations, and it means 2 decimal places. And here trash, what is this? It determines the threshold for text color contrast. And iterates here product range, what is this? It iterates over all cells in the confusion matrix. And plot text, what happens here? It adds text to each cell with color determined by the threshold to ensure readability. And here we have a labels, Y label and X label. And let's continue and let's switch. It's okay. What happens here? We will load the label data from a file profile.txt and read the file as a CSV using tab here, separate tab, and as the delimiter without any headers, and label columns here: cooler, valve, pump, accumulator, flag, and it assigns column names to the data frame. And here let's look at the data and df parts. We will load multiple sensor data files into a single data frame, and it is a list of sensor data files and df dot df equal pd dot data frame. It initializes an empty data frame, and we have a loop here. What happens here? The loop iterates over each file name in the data list, reads the file into a data frame and appends it to the main data frame, and we will print it. And here we can see the shape of the data frame. It is the total number of rows in the data frame representing all the combined cycles from the sensor data files. And secondly, here the number of columns indicating that each cycle has 6,000 data points recorded. And what we can say here, it is the auto shows the first 5 rows of the data frame with columns labeled from 0 to 5,999, representing the pressure readings for each cycle, and each row contains the pressure readings from the sensors over time. And let's switch here. We will reshape the concatenated data frame to organize the data by cycles and sensors. And what we can say here as df sort index here, it sorts the data frame by its index to ensure the data is in the correct order. And values, what is this? It extracts the underlying numpy array from the data frame and reshape -1 length data length df columns. What happens here? Here -1 is used to enter the correct dimension size automatically, and transpose part, it transposes the array to have dimensions, effectively reorganizing the data structure, and we will print it. And here number of cycles, here number of readings per cycle, and number of sensors here. And we will visualize the original pressure data from the sensors. Here it creates a figure with the specific size, and here it plots the pressure data for the third cycle and plot cycle original pressure sickness. What happens here? It says the title plot and y label and x label pressures and time. And what is this? It configures numpy print options. And let's look at our plot and talk about it. The plot shows the pressure readings from 6 sensors over time for the third cycle, and the y-axis represents time with each unit corresponding to the pressure reading, and y-axis represents the pressure values recorded by the sensors. And we have different colors, and these different colors in the plot represents the pressure readings from different sensors. And the pressure signals have distinct patterns, with some sensors showing higher pressure values and others lower. And as the plot reveals the variations and trends in pressure over time, providing insights into the behavior of the hydraulic system during the cycle time. And let's switch. Let's continue to our code. Okay, let's look at this part. Apply clipping. What happens here? we'll apply clipping and compute the first order difference of the pressure thickness. And what happens here? First, MP diff. Let's look at this. What happens here? And df and x is equal 1. It calculates the difference between consecutive values along the second axis for each sensor. And np.clip and minus 5 and 5. What is this? It clamps the values to the range to limit extreme variations. And this step helps to normalize data by emphasizing changes in pressure while suppressing outliers. And here we can see the output. The number of readings per cycle is now 5,999. And again, we have a plotting part for standardized data. We will visualize the standardized pressure data after applying clipping and differencing. And again, plot figure and plot part. I mean here plus the standardized pressure data for the third cycle. And again, title, variable, xable, and print options part. And let's look at our plots and talk about this. The plot shows the first order differences of pressure readings from 6 sensors over time for the third cycle. And here the x-axis represents time with each unit corresponding to the pressure readings, and here first difference, I mean y-axis represents the first order difference values indicating changes in pressure between consecutive readings. And what we can say for that plot, the pressure signals show variations with some spikes indicating significant changes in pressure over time here. And clipping has limited extreme values to the range. It's minus 5 and 5, making the data more uniform and emphasizing normal variations. And I think it's okay. And let's look at our other parts. Here we will look at the distribution of label, and we can see some values. And we are focusing on the accumulator column from our label data frame, as you can see here, label.accumulator. And label.value count here gives us the count of each unique value in the accumulator column, indicating how often each condition occurs. And we have some numbers, 90 and 130, 115, 100. What is this? It represents different states of the accumulator's condition, and the count text to each number shows how many samples belong to each state. And let's switch to label mapping block, and let's talk about this. What happens here? We create two dictionaries here, this label, this reverse, and what are they? This label maps the original label values to the integers, and this reverse label maps these integers back to the original labels. And we have a loop here. What happens here? The loop for I lab in enumerate label unique, it iterates our unique labels, assigning each a unique integer, and label equal label map here. What is this? It transforms the labels into the data frame to their integer equivalents, and y equal to categorical label. It converts to the integer labels to a one-hot encoded format, which is suitable for training machine learning models. And let's switch to our spectrogram transformation. Here we transforming our time series pressure data into spectrograms. A spectrogram represents the spectrum of frequencies of a signal as it varies with time. And let's look at the code. DF spectra here first. What happens here? We create an empty list df underscore spectra to store our spectrogram data, and here we have a for loops. And what happens here? First, look at this TQDM part. We look through each sample in our data sets, df using TQDM to display a progress bar for this potentially time-consuming process. And we will apply spectrogram transformation. For example, we use NP apply along axis. Here, as you can see, LibRosa feature mass spectrogram function along each axis of the sample. The mass spectrogram function from the LibRosa library converts our pressure signal into a mel scale spectrogram here. And what we can say here, sample part, sample spectre. Can we talk about this? Yes. Here we append each spectrogram to our list and convert this list to a numpy array for easier manipulation later. And let's look at these parts. df spectra equal np as array. What is this? We append each spectrogram to our list and then convert this list to a numpy array for easier manipulation later. And let's look at the output shape. After transforming all samples, we print the shape of the resulting array, and the shape, as you can see here, indicates we have 2205 samples. Each represents as a 128 and 12 6 array. I mean here 129 mel bands and 12 time frames and 6 sensors here. I hope you understood. And here we will visualize the spectrograms of a sample for each sensor using LibRosa display spec show here, as you can see. And this helps us see the time frequency representation of the pressure signals. And we have 1 2 3 4 5 6 6 plots. And what happens here? What we can see, x-axis represents the time and y-axis represents frequency bands, and what are the color intensity represents the amplitude of a particular frequency at a given time. And here these visualizations help us understand how the frequency content of the pressure signals changes over time. For example, you can see that. And it is important for detecting patterns and anomalies in the data that might indicate faults or failures in the hydraulic systems. And let's switch and let's talk about our splitting parts here. I think I switch. Okay. Train test split here. This function from scikit-learn.model selection splits the dataset into training and testing sets. You already know that. And what are the parameters? df spectra, the input features, which are the spectrogram, the transformed pressure signals, and here y, the labels corresponding to the status of the accumulator, and random state, you know, that ensures that the split is reproducible. And test size 0.2. It allocates 20% of the data to the test set and the remaining 80% to the training set. And this step is important for evaluating the performance of the model. By splitting the data, we can train the model on one subset and test it on another, ensuring the model's predictions are evaluated on unseen data. And now we'll define our CRNN model, and let's talk about it. We have a function called getModel. This function defines convolutional recurrent neural networks for classification tasks, and input layer. What happens here? I mean input shape data shape 1, and data shape 2, and data shape 3. It defines the input shape of the data. And let's look at the convolutional layers. First, convolutional 2 dimensions. It applies 2-dimensional convolution over the input data to extract special features and parameters. Filters equal 64, number of the output filters, and kernel size 2 what is this size of the convolutional window, and padding same. It ensures the output has the same width and height as the input. And here we have permit layers 2, 3, 1. And what is this? It changes the order of dimensions, and batch normalization axis equal -1. It normalizes the activations of the previous layer at each batch. For example, applies a transformation that maintains the mean activation close to 0 and the activation standard deviation close to 1. And permits here 3, 1, 2. What is this? It changes the order of dimensions back to the original configuration. And activation value, what is this? Applies the value activation function and max pooling 2 dimension. And here pool size equal to 1. It reduces the spatial dimensions of the output and dropout 0.2 randomly sets 20% of the input units to 0 at each update during training time, which helps prevent overfitting. And reshape and recurrent layers parts. Let's look at the reshape. It flattens the output to fit into the GRU layer, and bidirectional here GRU 64 activation value return sequences false. And what happens here? It is a bidirectional GRU layer that reads the input in both forward and backward directions, and thus 32 activation value here fully connected layer with value activation, and dropout 0.2, another dropout layer to prevent overfitting, and output layer finally dense white rain shape 1 output layer with softmax here activation for multi-class classification. And we will compile our model. This model structure is designed to handle both spatial and temporal aspects of the input data, making it suitable for time series classification tasks where the input data is transformed into spectrograms. And let's look at the get model extrain, and let's look at our model summary part and talk about this. Switch. Okay. Here we will see our summary of the models, and this generates the model summary showing each layer's type, output shape, and number of parameters. And the model has a total 1,600,000. It's really big parameters, all of which are trainable. And let's look at our early stopping parts, and let's look at this. What is early stopping? Here it monitors the validation accuracy and stops training if it doesn't improve for 15 epochs, restoring the best weights. And model training part trains the model on the training data with early stopping, validating on 10% of the training data. The training progress is printed for each epoch, showing loss and accuracy for both training and validation sets. And you can see here it is long, and let's switch. Okay, and let's make some predictions on datasets and talk about this switch. This lines uses the trained model to make predictions on the test data, and the predict method returns the predicted probabilities for each class, and NP arc marks here. What is this? This function is used to get the index of the class with the highest probability for each prediction, which gives the predicted class labels. And we will print our report here. These lines prints a classification report that includes precision, recall, advanced score, and support for each class. You know that we'll talk about it before. And what we can say here, we have a confusion matrix visual part here, and we can talk about this. This lines calculates the confusion matrix, which shows the number of correct and incorrect predictions for each class, and the confusion matrix function from scikit-learn matrix is used to create the confusion matrix. And plot figure size part, you can change the parameters. And finally, here we can see confusion matrix, and what we can say here. And let's talk about this. First, x-axis is predicted label. This represents the labels predicted by our model, and y-axis, this represents the actual labels, and each cell in the matrix represents the percentage of predictions, and the values are normalized such that each row adds up to 1, making it easier to interpret the accuracy per class. And here diagonal values, what we can say here, 130 and 130 here. For example, it is 91% of the samples that were actually 120 were correctly predicted as 130. And let's look at here 115 here 115 and it is 63% of the samples that were actually 115 were correctly predicted as 115, and 100 here 88% of the samples that were actually 100 were correctly predicted as 100, and finally here 92% of the samples that were actually 90 were correctly predicted as 90. And in the same way, you can examine another cells, and you can see them. The confusion matrix shows that the model has high accuracy for most classes, especially for the 130 and 90 classes, and there is some confusion between the 115 and 100 classes, indicating that the model has difficulty distinguishing between these two classes. Overall, the model performs well with an overall accuracy of 86%. And if you want, you can examine our reports, and you can see our values, and values performed well, as you can see here. We talk about the precision recall advanced score previous lesson, and I think it's okay for our CRNN lesson. Thank you so much for your listening and attention. I know class is long, but the project is long. Anyway, see you in the next class.